Okay. So, last class we talked about existence of giant emergence of giant component in random networks, and now let us first try to give a more informal logic of existence of giant component in any arbitrary existence of giant component in any arbitrary random graph. Okay, means a random graph with any arbitrary degree distribution. Okay, a random graph with any arbitrary degree distribution. So, what can be the logic? See, you have a node is visiting its neighbor. Okay. When can you say that a giant component exists? What is the size of a giant component? Is order of the size of the vertices of the whole network. So, if the entire network is infinite, what should be the size of the giant component? It is also infinite. Okay. So, it is also giant component is also infinite. Okay. Clear? So, now let us think that I am in a node A and I am in a node, I am going to a node B. Okay. I am in a node A and I am going in a node B. So, when can I say that I am a part of an infinite graph or infinite connected graph? Can you tell me, if I go from a node A to node B, when can I say that I am part of an infinite graph?
B is connected to some other nodes.
Yeah. So, what happens is B would be connected to some other node. So, that is say Ki, B has a degree Ki. Okay. B has a degree Ki. Okay. So, what happens is, if it is always expanding, so number of if I am going from A to B, how many nodes I explore? I explore one node. Okay. And by exploring one nodes, what are the how many new nodes I have possibility to explore? Huh? Ki minus 1, because I am coming from. So, basically think that I am coming here. So, I am already exploring one node. So, that is the cost I am incurring, and after incurring this cost, what is happening? I can explore Ki minus 1 new nodes. Okay. And so, what should happen is that this Ki minus 1 should always be greater than 0. Okay. And there is one more thing, important thing. If I am of degree k and if I am of degree 1, okay, there are two possibilities. I am of degree k and I have degree 1. Okay. There are two cases. So, now what is the possibility that I would be I would reach a degree k than a degree 1. I have k times more chance of reaching a degree k than a degree 1, because if I start from any of these kth neighbors, I can reach it. While reaching here, I have just only one possibility. I have just only one possibility. Okay. So, that is why I also have to have this joint probability that Ki and Ki minus 1 minus 1.
So why there is extra minus 1, Ki minus 1 minus 1?
This extra minus 1 is that, see, when I am coming from A to B, what I am spending, how many nodes I am spending? I am spending one node. Okay. And by spending this one node, what are the possibilities getting open to me? K minus 1 possibilities, because this has node degree ki, so ki minus 1 possibilities. So, what is happening? Ki minus 1 minus 1.
-1 for A.
Because B, I am exploring B, no, I am already spending B. So, that minus 1, and B is giving me Ki minus 1 new nodes. So, it happens for all i's Ki minus 2 greater than 0.
What do you call this in this Ki minus number of possibilities? The number of
It's a degree. Ki is degree of the ith node.
what is summation that you taking Ki? That is the number of nodes you can visit.
For all i's, I have to take for all i's. It should be for all i's.
So what is the logic behind introducing the
Huh?
So what is the logic behind introducing the first case? Like why you are taking the joint distribution?
Why Ki? Because I am taking this joint distribution because I am telling that if Ki has high degree, then I have more possibility of coming to Ki from a neighboring node, and if Ki has low degree, then I have less possibility. So, while I am exploring or while I am doing a walk, I have always the chance of reaching a high degree node than a low degree node. So, that should be taken into consideration when I am thinking of an expanding graph. So, I am thinking of an expanding graph, that I am coming from one node to the second node and second node to third node this way. And what does giant component means? That if I go on exploring, it will be an infinite component. Okay. So, this is the formula. We will come to a rigorous analysis of this, but just from first principle, let us try to understand that this will be the formula. Okay. So, for rigorous analysis, we will actually use generating functions. Okay. So, for rigorous analysis, we will use generating functions. So, I hope generating functions, you have idea of generating functions. So, what are generating functions? Orithro, what are generating functions? Okay. So, it is the function where the, so I try to write. So, P0 x, P0 plus P1 x plus P2 x square plus Pn x to the power n, and it goes on. Okay. So, if this is a generating function, what does this mean? That each coefficient of this polynomial is encoding some information. Okay. So, it is a function or it is a series or it is a polynomial, you can tell it in various ways, where each coefficient actually encodes some information. Okay. So, let me think that what will be the generating function of a graph. I want to represent a graph by a generating function. So, my now objective is generating function and graphs. So, the simplest thing by which graphs are represented are degree distribution. Okay. So, degree distribution, or rather I will say I will basically represent degree distribution of graph through generating function. Okay. And you see this is how you can represent. Okay. So, where p k or p n is that probability that their probability that a node will have degree n. Okay. So, basically you can write it in a more compressed form. Okay. Probably you can write in a more compressed form G 0 x is equal to p k x k. Okay. So, now what is the importance of writing the generating function? So, tell me from these generating functions you can really find out many characteristics of the graph very easily. So, what is G 0 1? G 0 1 is equal to p 0 plus p 1 plus p 2 plus p n and it becomes 1. Okay. Clear? So, G 0 x is equal to 1. It should be 1 if it is normalized well. Okay. Okay. Tell me now I want to find p k. I want to find p k from G 0 x. So, how do I find p k from G 0 x? Okay. So, let us try to find p 0. If I want to find p 0, what way is it? G 0 x is equal to 0. P 1 tell d d x of G 0 x at x is equal to 0. Okay. So, p k is equal to and you have to have some okay. Clear? So, you get p k p 0. So, from the generating function you can directly get the probability that a node will have degree k. Okay. Okay. Can I proceed? Okay. So, now let us say what will be z? Z is k, okay, average degree. I want to find out average degree. So, how do we represent average degree? How can we represent average degree? Huh? No, tell me the formula of average degree. Okay, it is summation of k p k. So, that is, if you again see this generating function, see it and tell me what will this be? Huh? Yeah. So, G 0 dash 1. Okay. Basically, if you have G 0 dash 1, it says 1 into P 1, 2 into P 2, 3 into P 3, n into P n. Okay. So, from the generating function immediately you get the clear? Karishma, not clear? So, z is equal to k is a summation of k p k, that is clear? That is clear. So, then what happens is, if I differentiate g0 dash x, what is happening? Let us differentiate g0 dash x. This is becoming 0 into p0 plus 1 into p1 into x to the power 0 plus 2 into p2 into x to the power 1 plus n into pn into x to the power n minus 1, okay, and put x is equal to 1, then this becomes 0 into p0 plus 1 into p1 plus 2 into p2 plus n into pn, and this actually is summation of k pk for all case. Okay, agreed? Okay, clear, very good. So, now I want to proceed a little bit and I want to find out the nth moment. So, that is basically summation of k to the power n pk. Hmm? I want to find the nth moment. So, this is the first moment, no, z is the basically first moment, okay. Z is first moment. Now, similarly I can try to find nth moment. Nth moment is this one. So, how to get it from the generating function? Very good. So, x d dx so every time you multiply x power base 1 less, every time you differentiate x's powers get 1 less. So, then you multiply x once. So, from this step, see from this step, if I have x, it will become 0 into p0 into x plus, anyway this does not have any meaning because it is 0. So, 1 into p1 into x plus 2 into p2 into x square plus n into pn into x to the power n, and again differentiate this entire sequence, then you will get back this 0 square p0 plus 1 square p1 x to the power 0 plus 2 square p2 x to the power 1 plus n square pn x to the power n minus 1. So, if you want to go one more step, again multiply by x, okay, simple. Okay, so what is it showing? What is, I go back to the basic. What is basically g0 x is showing? Is the degree distribution of, it's a degree distribution of a graph. So, it is actually showing the probability of, it is a distribution of a single node's probability of having how much, how many nodes, how many neighbors, okay. Single nodes probability distribution of having how many neighbors. So, now I ask you one question, that I do not want for single node, I want for two nodes together. Can you tell me the degree distribution given two nodes together? So, degree distribution given two nodes together. So the question is simple, that you want degree distribution of two nodes together. So first of all, what can it be? That two nodes can be thought as independent. Okay. If we think two nodes are independent nodes which has no correlation among them, then what will, if I say that is G 0 x, that will be basically, it will be G 0 x whole square. Think, let us write, this is P 0 plus P 1 x plus P 2 x square, this way it goes, and the second also I write P 0 plus P 1 x plus P 2 x square. Okay. So now do the multiplication. Do the multiplication. What happens is P 0 square. What happens in x? Let us see. Okay. So P 1 into P 0 plus P 0 into P 1, okay, plus x square, plus x square is P 2 into P 0 plus P 1 into P 1 square plus P 2 into P 0 plus P 1 and P 0 into P 2. Okay. So this way things go. Now let us think that if I have tried to find the degree, find the number of nodes with degree 1 summation. If I want to say the probability that when two nodes taken together the degree sum will be 2. Okay. I am asking this question, probability that when two nodes taken together the degree sum will be 2. Okay. So how will that happen? How can that happen? If I have node 1 and node 2, node 1 have 0, this 2, 1 1, 2 0. This is the possibility. So what is the probability that node 1 has 0 and node 2 has 2? What is the probability that node 1 has 1 and node 2 has 1? What is the probability that node 1 has 2 and node 2 has 0? See, exactly that is coming from the coefficient of x square.
So what is meant by independent over here?
It's, this is independent means, see, there can be a possibility like this, that this has degree 2 and this has degree. For this case it does not matter, basically this has degree 2, this has, for this case it does not matter, but it will matter for independent, that when I want to say that what is the number of neighbors when two nodes taken together. For this case it really does not matter, but if I want to ask this question that what is the number of neighbors when two nodes taken together, then it may not be exactly this. Okay. So this is just the number of edges going, but if I want to convert it into number of neighbors, then it will not be exactly this. Then you have to consider the independent concept. Okay. So, is this clear? Anybody has any doubt? Okay. So, this way things can be extended, and what we can say, if I consider m degrees together, if I consider m nodes together, then G0 x m will be basically G0 x to the power m. Okay. G0 x m will be basically clear. Anybody has any problem? Okay, very good. Okay, now we proceed in a. So, what we have said, what is G0 x? That if I pick up a random node, basically G0 x is showing what? If I pick up a random node, what is the probability of that node? Means what is the distribution of the probability of that node? Okay. Now, I want to think that I will not pick up a random node, but I will pick up a random edge and go to a random node. Okay. So, I want to go to a random node by traversing a random edge. Okay. Then how does it differ? It will be pk, but also it will depend upon k, because if I am, if I want to reach a k degree node, it depends upon the presence of k degree and also depends upon the number of neighbors. The same concept which I told last, that if I have more neighbors, I have chance of reaching a k degree node. If I have less neighbor, I have chance of less chance of reaching a k degree node. So, this becomes kpk. So, it becomes kpk. Okay. So, if I want to say that I want to have G1x, G1x is that outgoing degree distribution of a node reached by a random edge. Okay, outgoing degree distribution. So, that will be what? Kpk into, if it is a k degree node and if it has reached from a random edge, what will be the outgoing degree because it has already reached by one edge x, so k minus 1. Okay. And you have to suitably, because kpk would become more than 1, you have to suitably normalize it with summation of kpk. Okay. Okay. So, then I can write G1x is equal to 1 by z summation of kpk x to the power k minus 1. This becomes z. Summation of kpk is z. See, it is clear or not? Okay, I try to repeat once more. Okay, I repeat once more since this is little involved. So, I hope this part is clear up till m. Okay. Now, what I want to say that still now what I have done, I have picked up a random node and said what is the probability distribution of this random node. But now, what I want to say is that I pick up a random edge and go to a random node, then what is the probability distribution of this random node. Here we can think that if I have to reach a k degree node, it is not only depending upon its existence, which is denoted by pk, but also number of possibilities you have to reach that node. Okay. So, if you have a 1 degree node, you can just pick up one edge, but if you have a k degree nodes, you have k possibilities. So, immediately that multiplies. So, then you have the joint probability joint dependence k into pk, and that can be encoded. So, then I want to ask, okay, I want the outgoing degree distribution, not the distribution, not the degree distribution, but the outgoing degree distribution. So, outgoing degree distribution means I have already reached by, I have picked one edge and come to that node. So, I have to subtract that. So, then what is that happen? That is why the power becomes a k minus 1, and suitably I have to normalize. So, summation of k p k is equal to z. Okay. So, then it becomes 1. So, now I write it in a generating function from. So, g 1 x is equal to summation of k p k x to the power r. Yeah, we come, it will be the first neighbor outgoing. So, very good that what is happening, you are at a node, you come here and you then have the outgoing degree distribution. So, if this is g 0, this is g 1. Okay. I am seeing one step ahead. So, that is why we name it g 1. Because I have the outgoing, so x to the power k is always denoting means I have what p k x to the power k. So, the coefficient of x to the power k is showing the property of the kth degree node. Okay. And now, what I am trying to model? I am trying to model the property of the outgoing degree distribution. Okay. I am trying to model the property of the outgoing degree distribution. So, here the outgoing degree distribution, in terms of outgoing degree distribution, a k degree node is actually a k minus 1 degree node. So, it is actually representing the property of a k minus 1 degree node, because I am considering the outgoing degree concept. Okay. So, that is why it comes k minus 1. So, this we can, what will be this? Okay. This becomes 1 by z g 0 dash x. Okay. So, now the next question which you can ask is that you already have a you know g 0, you know g 1. Okay. You know g 0, you know g 1. So, I want to say, I want to find out what will be the distribution, what will be the degree distribution of the second neighbor, of my second neighbor. What will be the degree distribution of my second neighbor? Okay. So, the probability distribution of the number of second neighbors of the original vertex. I was here, I picked up a random edge, came here, and I know this. So, what is the probability distribution of the number of second neighbors of an original vertex? So, that again becomes pk into g1 x to the power k. I know this, I have k. So, think from here, I know this one, okay, g1, and I have k neighbors. So, all g1, 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 okay. If I am g0, I know g1, okay. I know the distribution of g1, okay. Now, I can have k g1s because I have I have k degrees. So, what will happen? What is the probability I have k degrees? Pk, and for all this it will behave independently. Now, as Arithra was pointing out, now independence is important, because there can be possibilities that you can have something like this. Okay. So, for simplicity we are thinking that it is independent, that this possibility does not exist. Okay. So, you get this. Okay. Okay. So, this gives basically, what is this basically? Tell me what is this in terms of g0? No, tell me what is g0. Tell me what is it in terms of g0. So, g0x is, I write summation of pk x to the power k. So, what is this?
G0 G1.
Very good, g0 g1x, because I am just replacing x with g1. Okay. So, yeah, this independent, about this you can see there is a good work by Joydeep, who has just shown that if it is not independent, how to calculate and how to adjust this equation. Okay. Okay. So, is this clear? Is this clear? Okay. So, now let us find z2. What will be z2? So, z1 is z, okay, first neighbor. Now, second neighbor z2. What will be z2? How did we find z1? What was the formula of finding z1? This is the formula of finding z1. So, z2 will be d dx this is how generating function goes, no? Okay. Clear? And what will this be? So, g0 g1x and it will be g1x outside g1x and g0 dash g1x. This thing comes outside, and okay, and this is, and x is equal to 1.
Basically, that will be G1 dash x G1 dash. The left term will also be indifferent.
What? This one G1 dash x. Okay. So then this becomes G1 dash 1 into G0 dash G11 is G11 will be any generating functions. If I just put 1, it will be no. We said G01 was what? 1. So G11 will also be 1. Any generating function, if I just put 1, then it is just P0 plus P1 plus P2, which is summing up of 1. So G11 is also 1. So this becomes 1. Okay. And what is G0? First, what is G1x? What is the formula of G1x? We studied. Tell me the formula of G1x. So, this is the formula of that 1 by z. What is z basically? Z is basically G0 dash 1. Z is G0 dash 1, if you remember. Okay. So then let us write this. Okay. Back, it is G0 double dash x double dash 1 into G0 dash 1 into G0 dash 1. So this gives us G0 double dash 1. Clear? This one. So because I have G1x and here I have G1 dash 1 or I had G1 dash x. Okay. So this will become double dash. Try to see this. You have G1 dash x. See this. Okay. You have G1 dash x. This part. I am trying to think about G1 dash x. I know G1 x. This is G1 x. So from here, tell me what will be G1 dash x. G0 double dash x by, this is a constant, this is a z. Okay. Okay. Clear? So that I have just put here. Again replacing x by 1 I have put here and I get this. Just replacing G, now I am putting G0 dash 1 and this z again I am writing as G0 dash 1 double dash 1 and this is G0 dash 1 and it gets divided. Whether? Okay. So if we can once more think and just revise why Z2 comes. Okay. So let us see in this way. What happened is we have understood G1 x. What is G1 x? G1 x is, if I am coming from a random edge, then what is the degree distribution, outgoing degree distribution. Okay. And then I say that I come from a vertex to a random edge, and so we say that this is G0 and this is G1. Okay. Now I am telling that I have k degrees. So what will happen? Peak. So if I want to find the second neighbor, I have to consider all these k degrees as independent, and this becomes G1 x to the power k, and the probability I have of k degree is pk, and this becomes G0 G1 x. So what is this showing basically? Semi probability distribution of no of my second neighbor, not outgoing edges of my first neighbor. These are outgoing edges of the first neighbor. So, of my second neighbor. I have thought simply that all these outgoing edges goes to distinct neighbors, distinct nodes. That is my assumption. You may criticize. Probability distribution of my second neighbor, or I can say probability distribution of the outgoing degree of my first neighbor. Okay. You can outgoing degree of the sum of the outgoing degree of my first neighbors. Okay. Probability distribution of the sum of the outgoing degrees of my first neighbor, or you can say probability distribution of my second neighbor. Yeah, means of the number of second neighbors. Okay. Means here if I try to say that, okay, let us think in this way. Let me take a new thing. So, you have G0 G1 x, that is say again something like this, and which is given as Q0 plus Q1 x plus Q2 x square, means if you suitably do it, it will come like that. Okay. So, what does Q2 means? Tell me. What is the probability that I have that a random node, a node picked randomly, a node, okay, I write a node picked randomly will have 2 second neighbor. Okay. A node picked randomly will have 2 second neighbors. Clear? So, now is this clear? So, what will this give basically? It will give again Q0 plus 1 into Q1 x, I say x is equal to 1. So, 1 into Q1 plus 2 into Q2 plus n into Qn, which is basically the average. Okay. So, that is what I say, that is what we say set to. Okay. The average second neighbors I will have. Okay. Is this clear? So, then once this is coming, once you have this concept, the other thing is easy, it comes simply from a little algebra. Okay. So, in this way you can go on finding the third neighbor, the fourth neighbor, you can find out. Okay. So, now let us come to specialized graphs and try to do this on specialized graph. Like if I take I am taking Poisson, okay, simple random graph. Okay. Okay. So, I take this simple random graph. Now, if I take this simple random graph, what is this? 1 minus p plus px to the power n. Okay. If I take this simple random graph, it is 1 minus p plus px to the power n. This is binomial. From here it directly comes it. See, this is not it's easy. Okay. Now, what we know? that NP is equal to Z. Okay. We know NP is equal to Z. No problem, NP is equal to Z. So, actually P is equal to Z by N. So, I can write this as 1 minus Z by N 1 minus x to the power n. Okay. No problem, and limit n tends to infinity becomes what? Limit n tends to infinity. Akshit, what does it become? Limit n tends to infinity? No. Why should it become 1? It will become e to the power z x minus 1. The same thing we did, that from Poisson you can. Okay. So, now given this, what we want to find? First of all, we want to find is G1x. So, let us try to find G1x. What is G1x? Tell me the formula quickly. What is the formula of G1x? G1x is 1 by z z0 dash x. Okay. So, differentiate this 1 by z d dx of e to the power z x minus 1. So, that gives us 1 by z into z into e to the power z x minus 1, and that is again e to the power z x minus 1. So, this is a, so you see this is a special type of graph where if you come from a random node, if you pick up a random node or you pick up a random edge and go to a random node, both are yielding same degree distribution. So, random networks are something where you can pick up a random node or you can go from a random edge to a random node and it will have same degree distribution. Okay. So, we will continue with this on other type of networks, and also we will try to find out the second neighbors etc. in the next class. Thank you.